Hello, welcome to the OneClass channel. My name is Fajori Rome, and I am an Honors Bachelor of Science student currently working towards medical school. Today we'll be going over some commonly asked chemistry questions at both the high school and college levels, okay? If you need some homework help or tutoring, you can definitely check out the links in the description below, so that way we can further assist you and really help you get those topics memorized and comfortable with. Alright, so with all that being said and our formalities out the way, let's kick off this session with our first question. Alright, so what we have here, it's asking us, what is a hypertonic solution? Okay, so what does it mean to be hypertonic? Okay, and we'll actually do that comparing three states. We're going to just say hypertonic, tonic, and isotonic and hypotonic. Okay, so with that we need three, I guess, glasses of water. Okay, well, some solution. Okay, so we're going to label this one hypertonic. We're going to make this one isotonic, and we're going to make this hypotonic. Okay, now the thing you have to remember though is that these hyper, iso, and hypo are going to be in relation to something. Okay, and that's the key part. It's going to be in relation to something else. Okay, so with that being said, we're going to add our something else in this. Let's think of just add a little ball there for each one. If you remember, think of that the egg experiment you did, where it's like, you know, when you put an egg in a certain type of solution, either the egg will shrivel up or it will expand, or even like the balloon one, for example. I'm pretty sure that's another one too. But the most common one is the egg, because the egg serves as a very good membrane where it allows relatively easy diffusion of water in and out, but nothing else. So with that being said, okay, we're going to start with the isotonic. Okay, iso, the prefix iso means same. Okay, so if you add solutes, which is going to be marked by these red dots, okay, it's going to be pretty much evenly spread out, as in there's no much difference between what's in the ball and what's outside. Okay, this is what you would consider like isotonic. I could take out the ball, okay, and the solution, in fact, that's what I'm going to do. I'm going to draw out the solution with the rest of them. I'm just going to add a circle. Okay, so this is what it looks like to be hypertonic. Everything is the same. Okay, inside the ball has around the same ratio as outside the ball, which is what they're referring to as the solution. So the solution in this case is isotonic to the ball inside. Now, hypotonic, okay, this means less. All right, so we're going to have here is going to be a difference. So we're going to have quite concentration inside the ball, okay, and it's going to kind of look like this. This right here would be a good example of hypotonic, okay, because the solution is less than what's inside the ball. And remember, this is all in relation to something else. Okay, hypertonic, you probably guessed, would be more. This is where the ball is going to look quite, in fact, I'm just going to draw like two of them in here, quite empty, and the solution is just jam-packed. Okay, this would be an example of a hypertonic solution. The solution has more solutes, so dissolved things, inside relative to the system inside of it, okay, which is going to be like that ball. So here we have the three distributions here, okay. Now if we assume that this membrane, okay, it's like the ball is a membrane that is only permeable, as in only, permeable means it can flow in and out, but it's only permeable to water, and that's a key part. To water, that means the solids can't go in and out. The only thing that can move in and out would be the water. Let's start with the isotonic solution, okay? If the membrane is only permeable to water, it has no reason to move, because everything is already the same. In the hypotonic solution, where it's actually less than what's the system inside of it, water will flow from the surrounding, so from the solution, into the sphere, because that way, when you have now a bigger sphere, it would end up looking a little bit more isotonic, because now you've given it a bigger radius with around the same amount of solids as it started with. So that would make exactly, so that's why water would flow in, okay, because it needs to make up for the concentration of solids. So if you even like did like ratios, for example, it's like A over water, that's concentration inside, and then the concentration outside would be like B over water, okay. So what we want to do here for the hypotonic solution is that we're going to increase the water here and decrease the water here, so that these two will end up equal to each other, because A and B do not change. The amount of solids inside and outside, those can't change, they can't cross the border. So that's what's going to happen there. You will take the water from the outside going in, therefore increasing the water inside of the system, and decreasing the water in the surroundings, okay. And what this does, when you increase the water in the system, you end up with a less concentrated solution, because like you're increasing the denominator. I mean, a less concentrated I guess system in there, because you've increased the denominator. And when you decrease the denominator here for the hypotonic solution, in regards to that, you've now made a more concentrated solution. Hence how you're kind of balancing these two out. Now for this, sorry, I'm just going to copy here. The reason why is because for this, in the hypertonic, it's going to be exactly that, but the inverse. So instead of it being where you're going to now, actually I'm going to label it here. So A is concentration inside system, and B is a concentration inside, concentration of solution, okay. So now the system is in dire need of decreasing the water to kind of match, okay. So exactly, it's flipped over now, and the water needs to be increased on the outside in order for these to match better, because here the B is already quite high, as you can tell. The concentration of solution is quite high relative to that. So in this case here, you actually see water flow out in a hypertonic solution. So I know the question was only asking about the hypertonic solution, but in order to really understand I guess all different types of tonicity, you need to go through all of them, because all of these are in relation to something else. What I did here is that it was system versus surrounding, solution being the surrounding and system being the inside of it. And so that is what we get here. So let's see how we did. Hypertonic solution is a solution that contains higher concentration, so that is correct, of solids compared to another solution. So that's why I compared it, where I put something in there. Sometimes you can also have examples where you draw it out like this, where you do have a membrane right in the middle that's also only water soluble. That's only water permeable, and then you have one side that has like this much, and this side that has like that much. Okay, so we have the more concentrated, so this would be the hypertonic, and this would be the hypotonic. You can also have it a split like that if it makes it easier. for you to see. So exactly, and the water will be flowing in and out through here. That's how it would work. But in this case, you would most likely see the water only go in this way because it needs to balance out this hypertonic solution. Okay, so with all that being said, let's see what else it says. If a cell is placed in a hypertonic solution, so that's what our ball is there, it's like the cell, there'll be net flow of water out of the cell, and the cell will lose volume. Exactly. And a solution will be hypertonic to a cell if its solute concentration, which is here, is higher than the inside of the cell, and the solids cannot cross the membrane. Exactly. If a cell is placed in a hypertonic solution, water will leave the cell and the cell will shrink, which is all explained in these different diagrams. So if you want to take a quick look at that, as I say, this is correct. You can pause the video even, just really take some nice notes. But other than that, let's move on to question 2. Oops, don't know how that happened.